So we did the first three, I believe. Is that right? Like we did the whole front. And I want you to add something up here at the top. We're going to add AP equals anchor points. Okay? Because we're going to put some anchor points on here, but I don't want to write the word anchor points over and over again. We're going to put AP, and then that way you remember what it means. Okay? I may also refer to them as key points. They're kind of the same thing. They're just the important points on our parent functions for when we do the transformations and whatnot. Now, for a linear, we're going to have anchor points here. I am not saying that we have to now graph lines in a complicated way. You can be graphing the lines the same way you've been graphing lines. But at some point when we're talking about these transformations, I want to connect the lines to it. Because I think that when you start transformations in Algebra 2, actually, you start them in Algebra 1 now, transforming the quadratics just a little bit. But then when you get more into it in Algebra 2, I don't think you necessarily realize that you've actually been doing that with lines all along. You just approach it differently so you don't even realize that's what's happening. So we'll have our anchor points, but that doesn't mean you always have to use them here. So those would be these three. Those are going to be like our three anchor points for a linear, and that helps us with transformations, which is what we're getting to. So our anchor points here, and we'll write these in a little, I'm going to make your t-table horizontal because I know you don't have a lot of room to write here. So those points would be when x is -1, y is -1, 0, 0, and 1, 1. Okay? So those are our three anchor points there. Some of them will have 3, some of them will have 5, some of them will have 2. You'll kind of know when you get there what to expect and how many there would be. Okay. Now remember, the idea of parent functions is that when you see the word's absolute value as far as tied to a function, then you should be able to visualize this is what the absolute value function looks like, the parent function in your head. And you should know what this looks like. Or if I give you this, you know what any one of these three pieces should produce the other ones in your little brain. Okay, so that you can then take that parent function and do the transformations that way. Our anchor points here are going to be, we're going to have 5 of these. These are our 5 anchor points. Okay, so when x is 2, y is +2. When x is -1, it's +1, 0, 0, 1, 1, and 2, 2. Because when we do transformations, you're not going to be able to just slap a v down on something kind of in the right spot. You're going to have to have at least 5 points plotted, and then the rest kind of goes with it. And these are the 5 points that are going to help us transform things around. Okay, we good? Yes? Okay. All right, quadratic. Again, we've got these points here. Right? So these are our anchor points. One, 1, and 2, 4. Now, with the exception of the anchor points, dang it. With the exception of the anchor points and the equation itself, the stuff that we filled in for these two, they're exactly the same, right? Because they have a lot of the same features, and that's an important thing to understand as well. Obviously, they're not exactly the same, or they'd be the same function. But they have a lot of the same features going on. That's why we can't just use like these 3 points as our anchor points, because they'd be the same for that one, and then we wouldn't get our shape exactly how we needed it. Okay, we all good on those so far? Awesome. So now let's look at the back. So we got our cubic. Parent function for a cubic would be f of x equals what? X cubed. X cubed. Okay, that's why it's called a cubic, right? The names make sense. That's a good thing. So our domain is -infinity to infinity, right? Because it's all of the x's. And so is the range, -infinity to infinity. That's something you should be able to come up with real easily on your own. What's your x-intercept? 0, 0. So then the y-intercept is 0, 0. Are there any extrema or critical points here? Point of inflection, good. There's not technically extrema, but remember I told you we're going to put the critical points in there. So we have this point right here, 0, 0 is a point of inflection. Now, we can abbreviate point as PT period, but you cannot abbreviate inflection because I got all kinds of weird things, even with the name and the instructions, like point of intention and weird things like that. So we cannot abbreviate if we don't even know what we're writing, right? We're going to write out that word until we got it down. Point of inflection. Now, I've had the same kinds of questions over points of inflection, so I want to make sure I, again, address it with everybody. Some people are confused why it isn't also a maximum or a minimum. Well, remember, maximum and minimum is where the graph changes direction, or it changes from increasing to decreasing. And this is just a change in shape. So like my graph right here, I'm increasing. I just slow down a little bit, hit that point of inflection, and then I speed up some more. But I don't change my direction, right? It's just kind of a bump in the road, like I slowed down a little bit. So that's why it's different, and it's not an extrema. Okay? Now, that being said, I just said this, it increases the whole time. So my increasing interval is from negative infinity to infinity, right? Decreasing interval, are there any? No. If I increase over the entire domain, then I can't decrease anywhere, right? So my end behavior, here are little sentences. As x approaches infinity, f of x approaches what? Infinity. And as x approaches negative infinity, what does f of x approach? Negative infinity. Are there any discontinuities? Nope. Is it even, odd, or neither? It is odd, because I can rotate it 180 degrees, or I can substitute in that negative x. All right, good deal. So then we've got our important points here. We're going to use this one. Now, if all I use is these three, those are the same three I use for the line, so that's not enough, right? I want to use two more. They're not even on the graph. Now, these graphs only go to 5. Most of the time when you're graphing, you have a lot more grid on there. So we're going to write them down even though I can't graph them. But your anchor points, so I'm not going to start at -1. I'm actually going to start at -2. And if x is -2, then what would y be? -8, because 2 times 2 is 4, times 2 is 8. It'd be -8. And then this is at -1, -1, 0, 0, 1, 1, and 2, what? 8. Okay? So these two aren't on the graph, but we need them to get the shape when we have it in there. Okay? We all good with that? Any questions? Cubics we did in Algebra 2, right? You did. Don't lie to me, because I know you did. All right. So then we have this. It's the square root function. So my equation is f of x equals what? Square root of x. See how that works? All right, so our domain here goes from 0 to infinity. Do I include 0? Yes, I do. My range goes from 0 to infinity. Do I include my 0? Yes, I do. Do I have any x-intercepts? Yes, 0, 0. Good. Do I have any y-intercepts? Yes, the origin again. Good. Do I have any extrema? Yes, I do. 0, 0 again. And what's that? Very good. Absolute minimum. Does it increase anywhere? Yes, from 0 to infinity. So does it decrease anywhere? No. All right, so our end behavior. As x approaches infinity, f of x approaches what? Infinity. Okay, so then can I talk about what happens when x approaches negative infinity? No, because it doesn't, right? It stops there at 0. So I had some questions on this, and and people said, well, do I put as x approaches 0, then f of x approaches 0? So we'll put what you think makes sense. It's either that or it's nothing, one of the two. And usually at this point we're talking about limits, which is a little bit different than end behavior. End behavior is just kind of like a specific little subsection of limits. And so we decided this year to just talk about end behavior here, which changes this up a little bit. So when I got to this myself, I was like second guessing myself, because to me, end behavior, everything I've ever done or understood about end behavior was way out at the infinities, right? So then as I was overthinking it, and I could kind of reason why we would use 0 there, I thought, well, maybe it's one of those things where, yeah, that's my understanding and how I've always done it, but that doesn't necessarily mean that's the only way it is, right? Kind of like that example I showed you the other day. Like if we stopped here, you would make some assumptions that wouldn't be true, right? Just because that's the only way you've ever seen it. So one of the reasons it's always very important for me that that I give you the correct definitions and the correct theorems, even when they're a little wordy and maybe a little confusing, because then you have them to go back to and think, okay, what does it actually say? And I'm not stupid. I know that you don't always go back and reread that stuff, but you can, and you need to learn how to do those things. Like, what does it actually say? And so that's what I did. I said, okay, I went and I looked at your notes and realized I didn't give you the actual definition of end behavior. I mean, it was a description, but it wasn't a definition. So in the textbook, to find the actual definition, the textbook says something like, you are looking for what happens to the function value as x increases or decreases without bound. So, does x increase without bound? Do you know what that means? That means nothing's bounding it or stopping it, right? So yeah, x increases without bound, right? That's why we can write this. Does x decrease without bound? No, because it stops at 0, right? So then I also Googled it, because you can say the same thing with different words. I wanted to see a different actual wording of the actual definition. And so then I found one that said, it's that what happens to the function value as x approaches positive and negative infinities, which is the same thing as increasing or decreasing without bound. They just actually use the word infinities. So it is way out there, just like I thought it was, right? So when you talk specifically end behavior, you're only talking about what's happening way out at infinity where we can't see. So when you talk about end behavior on this one, we're only talking about that one side, because there's not, yes, it ends, but it's not end behavior. Does that make sense to you? Now, there is a limit here, and so here's the other thing I want you to think about. As you approach infinity, you can only approach infinity from the left, because you can't get on the other side of it to come at it this way, right? And as you approach negative infinity, you can only go this way, because you can't get at it the other way. Can I approach 0 from either side? Yes, so we talk about the limits a little bit differently, which again, we're not at limits yet, but I want you to kind of see that. I also want to look at one that caused some confusion on the notes, and maybe that'll help kind of make this all make sense. So we had this picture here on the notes. You remember that? We were talking about end behavior, and we were okay with it approaching 0 in both directions, but some of us kind of got stumped here like, okay, but that bothers me. Like, this is an end also. Why don't I care about that? But this is middle behavior, which I'm not saying we never care about, but it's not end behavior. But if I ask you this, so here's an asymptote here at -2, right? So as x approaches -2, what does y approach? Negative infinity, that's one answer. Everybody agree with that? As x approaches -2, what's happening to y? What does it approach? Okay, so as x approaches -2 this way, y approaches what? Infinity. As x approaches -2 this way, what does y approach? Negative infinity. You see how it's not even the same thing and we're approaching the same number? Because that's when you talk about left and right hand limits. Well, you can't do that at the end, because you can't get on the other side of it, right? So that stuff's coming later. We don't have to worry about it right now. It's important, but that's why I said right now we ignore middle behavior. Only the stuff that you technically can't see. It is possible to approach something from different sides and get the same. So as x approaches 0 from either side, you see how y approaches negative infinity both times? Okay, and again, we'll get there. We're not there yet. It's just kind of a little preview. But that's why end behavior is just a piece of that. So when you're here, we only talk about this because it keeps on going. Because this stops and we can't go to negative infinity with x, we don't even do it there. Okay, we okay with that? All right, any discontinuities? No, there are none. Is this even, odd, or neither? Everybody's kind of stumbled on this one today. So remember, algebraically, if you're not sure, what you do algebraically is you substitute in negative x. So f of negative x equals the square root of negative x. And then you simplify it if you can. If you can get f of x, it's even. If you get negative f of x, it's odd. Can I simplify this? No. If I did take the -1 out, what does it come out as? I. So this would be I times the square root of x, which is not f of x and not negative f of x, and that's why we know for sure this is neither. Plus, visually, graphically, it does not have y-axis symmetry, and it does not have origin symmetry, so that's also why it's neither. Okay. All right, so then we look at our anchor points. We're going to use this one, and this one. So our anchor points are 0, 0, 1, 1, and 4, 2. Which function is this directly related to that we have already talked about? Look at the ones we've already talked about. Which one is it directly related to? It's a quadratic. How is this related? How are the quadratic and the square root functions related? Close. Starts with an I. So reflection, right? Okay. It's what? Okay, yes. All right, so yeah, so you're right. So the square root and a square cancel each other out, right? Just like addition and subtraction cancel each other out, yes? And when those things cancel each other out, they are called what? Starts with an I. Inverses, okay? So addition's the inverse of subtraction, the square root's the inverse of the square, and so forth, right? So these are inverses of each other. Algebraically, what do you do to find the inverse? Do you remember? Good, you switch the x and the y and then you solve for y, right? Okay, so we're going to go back and look at the quadratic. I'm going to draw something on there. I don't want you to draw it on yours because I don't want it to confuse you later because you'll go back and like, why the heck did I draw this stuff? So just stick with me and we'll be fine. So if I take this and I algebraically switch x and y and solve for it, I'm going to get the square root function, sort of. Graphically, when you take the inverse, it is a reflection in the line y equals x. Again, don't draw this, okay? So you start reflections in junior high. I don't know if you do y equals x or not, but in high school geometry, you definitely reflect in y equals x. And when you do that, whether they're triangles, rectangles, whatever, all you're doing is switching the x and y coordinates, right? And then in algebra 2, that's when you actually do it algebraically and find it that way. If I take this parabola and I reflect it in this line, don't draw this, then I get this, but like a whole lot better, right? And so that's what happens. But that's not the square root function, right? How much of that is the square root function? Half of it. Why can't I use the whole thing? Because it's not a function, right? When you take the square root, when you are solving, when you introduce a square root into something you're solving, what do you have to put on there? Plus or minus, right? And so this is the plus or minus. But to make it a function, we only keep the plus side of it, right? So if you were to graph the inverse and you didn't put, see, this isn't plus or minus, because if I did that, I'd get this piece down here, and it's not a function. But this is part of the inverse of the quadratic, okay? And understanding how those are built is important too, because again, guess what? These just switch places. Your key point, and then you have more, obviously, because you have more of the graph. But we good? Okay. So now look at cube root. Parent function. F of x equals what? Cube root of x. That's why it's called the cube root function, right? Which one is this directly related to? The cubic. Because if I reflected this in the line y equals x, and this reflected up, then it's going to look like the cubic function, okay? And I get all of this because the negative's fine when you have an odd root. Our domain here, we're going from negative infinity to infinity. The range, we go from negative infinity to infinity. Do I have any x-intercepts? 0, 0. Do I have any y-intercepts? Same thing. Do I have any extrema or critical points? Yes, the origin, good. So 0, 0, and what is this thing? Point of inflection, good. Does this increase anywhere? Do I have any increasing intervals? Yes, whole thing, right? So negative infinity to infinity, and that means there are no decreasing. And then my end behavior, as x approaches infinity, f of x approaches what? Infinity. And then as x approaches negative infinity, f of x approaches negative infinity. Are there any discontinuities? Nope. Is it even, odd, or neither? Odd. Good. All right, so our anchor points. These three, and then two more that aren't even on my graph. So I'm not going to start at -1. What do you think I'm going to start at? -8. And when x is -8, y is going to be -2. Good. And then -1, -1, 0, 0, 1, 1, and 8, 2. And if you look at your little anchor points for the cubic, what happened? X and y just changed spots, right? Because that's what happens with your inverse. Any questions at all? All this sound familiar so far? Yes, not brand new stuff? Okay, good. So let's look at this second piece of paper you have. Yes. Let's say the 6th. All right, so we have the reciprocal here. So my parent function we know is f of x. What do you think the rest of that looks like? Okay, what is x over 1? X. It's 1 over x. I figured that's what you meant. Okay, 1 over x, good. It's irrational, yes, very good. So 1 over x, it's the reciprocal of the linear, basically. It's a line that's been blown apart. All right, so our domain, even if we didn't know that, we can get domain. Is my domain going to be all real numbers? No, okay, there's a break in there. So I go from -infinity to 0, and then I go from 0 to infinity, right? Use my little union. My range goes from -infinity to, oh, not infinity, dang it. -infinity to what? 0. And then the union of 0 and infinity. X-intercepts, do I have any? Nope. Do I have any y-intercepts? Nope. Do I have any extrema? Nope. Do I have any increasing intervals? Nope, because look, this is decreasing, 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 and then even though it comes up here, it's still decreasing the whole time. So there are none here. It's decreasing the whole time, so it should match my domain then. So -infinity to 0, and then 0 to infinity. And then do we use the little union here or not? Okay, so we're being last year we were not very careful with always being consistent with our types of intervals and stuff that we were doing, and that was one thing we wanted to work on this year, is to be consistent with it so that they're all in the correct notation, because everything wasn't always in the correct notation. And so we talked about the decreasing intervals a little bit different, but in interval notation specifically, I was told, no, we don't use the U. And I wasn't sure why, and even some students asked me, and I was like, I don't have a good why, but I'll work on that. I hadn't had time to work on it. But I figured out this morning, you do use the, because what does the U mean? It means union, but it stands for and also. It's the union, which implies and. All it means is and. It doesn't mean we're doing anything fancy with it, right? And so it is supposed to be there. Now, I know I've told you no, and I never counted off for it. I did just kind of mark it out and was like, don't do that. So I'm undoing that. And I'm sorry, I hate undoing things completely, but I'll give you some grace on that too, getting back to where we're actually putting it. You don't ever put unions between ordered pairs, because I saw that from a few people. That's weird. No. Okay, but intervals, you do use the union no matter what, which makes a whole lot more sense. Okay, so then in behavior, as x approaches infinity, f of x approaches what? 0, good. And then as x approaches -infinity, f of x approaches 0. One's from the top and one's from the bottom, but it's still approaching 0. Any discontinuities? Yes, I have infinite discontinuity. Where? at x equals 0. And remember, your discontinuities, no matter what kind of discontinuity, it's at x equals something. Even if it's removable, you never write the ordered pair. It's always just x equals. Okay? Is it even, odd, or neither? Odd. Good. All right, so then our anchor points, we actually only have 2. But I'll explain to you why in just a minute. Those 2 alone, like all by themselves, not really enough to get me the good shape if I'm going to transform it around. But these 2 points are important. We have -1, -1, and 1, 1. But then what does this function have that the other ones we've talked about so far haven't? Asymptotes. It's discontinuous, and that gives us the asymptotes here. So we have how many asymptotes in this graph? 2. So we have 1 here, and we have 1 here. Right? So my asymptotes, oh goodness, hang on a second. Asymptotes, I have 2. The vertical one is what? How do I write that? Is it x equals or y equals? X equals 0, and then the horizontal one is y equals 0. Okay. Now, I've had some people tell me the wrong things today. So some of you may have seen this before and some of you haven't. But here's, you are in pre-cal now. You can't get horizontal and vertical lines mixed up. Like that can't be something you miss because that's just going to mess you up on a whole lot of other things. If you're using both, then you kind of get lucky. If you don't know the difference, you got them both anyway. But if you just have one of them, you could be totally wrong. Or if you had to go graph that line. So in case you've never seen this before, if you write a y, a lowercase cursive y, in cursive like you were taught in like 2nd grade. That may not be how you really write it, but like that's what's on the little handwriting papers. If you rotate that 180 degrees, you get a lowercase cursive h. The y equals lines are horizontal, always. Y equals is horizontal. If you take an x and rotate it around, what are you going to get? X is not that exciting. But if you break that up, you get a v, right? So your x equals are vertical. Your y equals are horizontal. Never, ever miss that again, ever. You cannot afford for that to be a mistake that you make. So any kind of little trick you can have in your head, because they're easy to mix up, right? You start reasoning through it, and then you don't even know what's true about it. But have some way where you are never going to miss x and y equals lines, because those are the easiest ones to write. Okay, we good? Awesome. So when we start transforming things, not only are our anchor points important, but our asymptotes are also. Because if I was to take this parent function and transform it around, like translate it around, then those asymptotes have to go with me. If my asymptotes are here and then my point ends up being right here instead of at -1, -1, then I don't need anything else besides the asymptotes because I know it's supposed to grow towards it like that. You with me on that? And that'll help you with the shape. Because we're not going to be able to just slop stuff down on the graph. You're going to have those anchor points and asymptotes there as well. Any questions here? Alex, you with us? Okay. All right. Exponential. My parent function for exponential would be f of x. Now, here's on this one, we have to actually introduce a number in order to write it, okay? The variable x, though, is going to be where when we write this? In the exponent. That's why it's called an exponential, right? So this one in particular, I mean, it could be 5 to the x, 7 to the x, 1,000,000 to the x. It doesn't matter. It could still be our parent function. But I have this graph here, and based on this graph specifically, what is the base of this exponential? 2. Because when x is 1, y is 2. So whatever to the first power gives you that. That's how you know for sure here. Does that make sense to you? So this would be f of x equals 2 to the x power. My domain goes from -infinity to infinity. Where does the range start? 0. Do I include 0? Yes, no. Do I ever make it to 0? No. So I do not include it. Because no matter what that exponent is, I am never going to get 0, and I am never going to get a negative number out of it, right? Okay. Do I have any x-intercepts? It's okay. No, I don't. So that's okay. None. What's my y-intercept? 0, 1. Good. Do I have any extrema? No. Is it increasing anywhere? Yes. from negative infinity to infinity, which means it's not decreasing anywhere. End behavior, as x approaches infinity, f of x approaches what? Infinity. And then as x approaches negative infinity, f of x approaches 0. Very good. Are there any discontinuities? Nope. None. Is this even, odd, or neither? Does it have y-axis symmetry? Nope. Does it have origin symmetry? Nope. That means it's neither. Then we have some anchor points. Always goes through 0, 1, right? Why will it always go through 0, 1 no matter what my base is? Anything to the 0 power is 1. So if that was 5 to the x, 5 to the 0 power is 1. 10 to the 0 power is 1. A million to the 0 power is 1. It's always 1. So that's going to be one of them. Then I'm going to use these two and this one. So my anchor points. So if I start out here and x is negative 1, so 2 to the negative 1 power gives me what? 1/2, because it gives you the reciprocal, right? So this is 1/2. Then when x is 0, y is 1. When x is 1, y is what? 2. And when x is 2, y is 4. Oh, I don't put y, dang it. 4. Sorry about that. All right, now, here, if that was 5 to the x power instead, the y values will be different, right? Because it's dependent on that base. The x values are going to stay the same. But if at negative 1, if that was 5 to the x power, what would this be? 1/5, right? It's just the reciprocal of it. And if that was 5 to the x, what would this be? Is this going to change? What's 5 to the 0 power? 1. Anything to the 0 power is 1. So this doesn't change even when my base changes. That base could be anything, and it's still going to go through 0, 1. Does that make sense? If this was 5 to the x, when x is 1, what would this be? What's 5 to the first power? 5, right? 5 to the first power would be 5 instead of 2. It would be whatever the base is. So would this be 2 and 10? No, it would be 2 and what? 25. Okay. So the x's would stay the same. These would change, but they're going to be obvious when we're doing these things and need to be transforming them. Hmm? If that was 5 to the x power and not 2 to the x, like if I change it, it could be, because it could be anything. It could be 7 to the x, 5 to the x, a million to the x, right? Yeah, no, not the same one. If it was 5 to the x, which it's not, but if it was, these stay the same, but these three would change depending on whatever the base is. Okay, we good? Now, are there any asymptotes here? Yes. This one right here, right? Okay. And so I have one asymptote. And what is it? Y equals 0, because it is horizontal. Y equals 0. We good? Don't do exponentials? Yes? Not brand new to you. Now look at the next one. It says exponential also. So how are these different or the same or whatever? Okay, good. So the power of negative x, because graphically, how are they, well, don't write that though. How are they different graphically? What happens to this one to get this one? Okay, it flips, which what's our big boy and girl rule for flipping? Reflex. It reflects in what? The y-axis. When you reflect in the y-axis, what changes? The x, the sign on x, right? And so that's why you get 2 to the negative x, but we don't actually write that, right? Instead, when you have that, we get f of x equals, since it's to the negative x power, it's the same as 1/2 to the positive x power. This is exponential growth and decay. When you have exponential growth, like we did up here, then the base is greater than 1. When you have exponential decay, your base is between 0 and 1. So it's some sort of fractional value there. Okay, we good? All right, but all that's really happening there is just a reflection in the y-axis. So our domain goes from negative infinity to infinity. Range goes from 0 to infinity. Do I include 0? No, I don't. Do I have any x-intercepts? Nope. Do I have any y-intercepts? 0, 1. Do I have any extrema? No. Is it increasing anywhere? No, that's why we call it decay, right? Is it decreasing anywhere? Yes, the whole domain, so negative infinity to infinity. And then we have our end behavior sentences. As x approaches infinity, f of x approaches what? 0. And as x approaches negative infinity, f of x approaches infinity. Good. Are there any discontinuities? No. Is it even, odd, or neither? Neither again. Good. So our anchor points are these. And so at negative 2, y is 4. At negative 1, y is 2. At 0, y is 1. And at 1, what is y? When the exponent's 1, what's the y value? It's 1/2. Do I have any asymptotes? Yes, we do. We have this, right? And that asymptote would be what? Y equals 0. Good. And so remember, when we do the transformations, that's going to go along with us. And that's going to be a line that if it goes, if it gets translated up or down, then we've got that to add. Okay? All right. We're not going to finish everything today. It's okay. But we can get through at least some of the next one. We'll at least start it. I want to start it. Or we can wait. You want to wait? We can wait. Oh, we're tired. Okay. We'll start here. But here's what I want from you, though. Even if you do not know, because I'm not giving you an assignment today, even if you're not sure what to write in here as the equation, you should be able to fill in some of these spaces. Would you agree with that? And so you do what you can do in there. That way when we talk through it, you're not having to write so fast. You can, and if you can't fill it all out because you're not sure, then don't fill it all out. That's okay, but you can't tell me you can't fill any of it out, right? Okay.